EE 496 Non-Invasive Blood Pressure Monitoring by Tony Graves, Pei Kwok, and Austin Tanaka. Faculty Advisor Olga Boric-Lebecki, Department of Electrical Engineering at University of Hawaii at Manoa. Early signs of cardiovascular disease, such as high blood pressure, are essential to disease management. However, many instruments used to monitor BP are invasive, uncomfortable, or non-continuous. According to recent developments in research, BP can vary throughout the day. Therefore, 24-hour monitoring of BP will help physicians to gain a clearer measurement of blood pressure. It could also help monitor the effects of a person's medication and determine if BP increases while sleeping. This would be difficult to perform using the conventional BP cuffs, which require stopping a person's blood flow every time a measurement is taken. The objective of this project is to study methods of non-invasive continuous blood pressure monitoring, focusing on the relationship between BP, pulse transit time, PTT, and pulse wave velocity, PWV, with piezoelectric sensors and Doppler radar. Previous research have concluded that PTT, the time it takes for a pressure wave to travel between two arterial sites, has an inverse relationship and can provide a non-invasive method of monitoring BP. PWV, the length between the arterial sites divided by PTT, can also be used. First, in our project we used piezoelectric sensors, which converts changes in the mechanical stress to voltage, were tested to obtain the pressure wave from the left bicep, wrist, and finger while resting in a chair. Then we continued to Doppler radar to obtain the pressure wave from the heart and piezoelectric sensors on the left finger while also resting in a chair. Continuous wave Doppler radar was considered because it has the simplest topology and the phase shift of the reflected electromagnetic wave is proportional to the periodic movements of the heart in a stationary subject. Materials used were piezoelectric sensors, BioPack, and Acknowledge software. First, we measured BP using cuff as reference. Then, the piezoelectric sensors detect displacement in arm. Then the output voltage was filtered through the BioPack hardware. Then the voltage peaks analyzed to determine pulse transit time. And finally, the pulse wave velocity was calculated. Materials and methods for Doppler radar and piezoelectric sensors. The continuous wave Doppler radar is transmitted at 2.4 GHz and the reflected signal is amplitude changed and phase shifted. That is mixed with the transmitted signal and goes through the quadrature receiver. The signal goes through a low noise amplifier and filter before being converted into a digital signal. Finally, the signal is processed by first linear demodulation using partial principal component analysis to choose I or Q channel signal. Then it is high pass filtered at 0.2 Hz to get rid of respiratory signal, low frequency noise due to leakage from local oscillator and components, and time delay due to filter. Peaks used to calculate PTT were visually chosen, and linear regression was used to calibrate PWV to systolic and diastolic BP. Results and analysis. The image shown here is the piezoelectric signal from the left bicep, wrist, and index finger. As you can see, the pressure wave peaks are clearly visible after filtering. The PTT and PWV was calculated, And as you can see, the bicep to finger takes longer time than the bicep to wrist or wrist to finger. Here is the raw piezoelectric signal from the index finger and the raw Doppler radar signal from the heart. Both signals were filtered as shown below. The blue signal is the radar and the red is the piezoelectric signal. The PTT and PWV were calculated. PTT ranges from 77 to 205 milliseconds and PWV from 12 to 5 meters per second. Summary of analysis. Comparing PTT from Table 1 and Table 2, the PTT increases proportionally as the length between arterial sites gets longer. Comparing PWV from Table 1 and Table 2, the PWV decreases proportionally as the length between arterial sites gets longer because PTT and PWV are inversely related. The standard error for a BP cuff is plus or minus 10 mercury, which is 7% error. Average error from Doppler radar and piezoelectric sensors using linear regression was 0.496% for a systolic BP and 4.16% for diastolic BP. From our research, we can conclude that Doppler radar and piezoelectric sensors have similar PTT and PWV values, and the average error is well below the standard BP cuff. Therefore, it is possible to use this process as a non-invasive and continuous method of monitoring BP. Possible future works. We could gather more data from subjects with different builds and health conditions, or try different positions like standing or lying in bed. Acknowledgements. Thank you, Ayako, Arjana, Linda for volunteering to be our subjects. Thank you, Isan and Makiko for helping set up the Doppler radar. This is Pei Kwok. Thank you for listening.